Hey all. So today I thought of discussing our pre-board question paper, and then I'm going to discuss few board questions in atoms and nuclei. Which one you want me to do first? Do you want me to do the atoms and nuclei discussion first, or the pre-board paper discussion marking scheme? So we have to give introduction about the Thomson model, isn't it? So this is a Thomson model. So why Thomson model? What are the drawbacks of Thomson model? So you have a positive sphere. The atom is considered as a spherical cloud of positive charge where electrons are embedded. It's also known as plum pudding model, isn't it? Why this model failed? Why this model failed? Any idea? It could not explain the
Stability of
hydrogen. Stability of
atom.
Stability, Rutherford. This one you cannot explain the spectral lines of hydrogen.
Spectral series. Yes.
Spectral series of hydrogen. Thomson model could not explain the spectral series. You know that electron from a higher orbit when it
emits the radiation.
When it goes to the lower orbit, higher energy transition occurs from when electron undergo transition from higher energy level to lower energy level. Radiations are emitted. The energy of the radiation correspond to difference between the energy level, isn't it? So
yes,
now there is no energy level in Thomson model at all, isn't it? Electrons are just existing as though plums are in the melon. In the melon, seeds are spread, like that. Watermelon seeds are spread. In that way, atom is considered to be a positive sphere, and electrons are scattered or placed everywhere. Okay. Of course, if atom is neutral, no charge, net charge, all this it could explain, but the spectral lines could not explain the spectral emission of spectral lines. Okay, then this is a very famous Geiger-Marsden experiment. Always tell the children, though it is a Rutherford, it was done by Geiger and Marsden, isn't it? Student of Rutherford, because in one of the board exam, this question was asked. Explain Geiger and Marsden experiment. What are the conclusion derived from Geiger and Marsden? Okay, so some students, they were not able to relate this gold foil experiment with that name. So always, whatever a scientist involved in the experiment, students should remember. And you are this gold foil, it should be a 1 atom thick. Why? Why this gold foil should be very thin? 1 atom thick, 1 or few atom only thick. That is the important criteria. So what are this? These are alpha particles, isn't it? Alpha particles, and this is a screen. What type of screen it is?
LED.
It's a fluorescent. This is a LED screen. This is the LED screen. This one is a LED screen. Alpha particle come out as a fine stream and strike the gold foil. So you have a rotating screen. It is coated with fluorescent material, and when the alpha particle impinge on it, scintillations. You know scintillation. No, you are getting that white yellow dot, isn't it? They are called scintillations. Beautiful diagram, isn't it? So now you can see that the alpha particles are scattered in all directions. But backward scattering only very, very less. Very less number of alpha particle underwent backward scattering. So this shift also very nice, because what is the observation from this? So these are all gold atoms. They're all gold atoms and alpha particles. Most of the alpha particles are going straight, no? Most of the alpha particles are going straight. But you can see some are deflected in the backward direction, isn't it? Some are deflected in the backward direction. Very few, very few. So if you have a electronic board, you can very well show that. During online classes, we can easily show, but with a board, we can show. Otherwise also we can show with a diagram on the blackboard, since it is there. So now, you know that when alpha particle strikes the gold nucleus head on, what happens? Here many alpha particle undergo deflection, which are alpha particles which are far away from the nucleus, isn't it? So what is the conclusion derived from this experiment? What are the conclusion? So most of the alpha particle are going straight, means most of this space in the atom is empty, isn't it?
Empty.
Empty.
Yes,
Most of the space in the atom is empty. They don't undergo any force at all. So only most of the space in the atom is empty. Very few undergo backward scattering like this. Very few backward scattering. What is the reason for the backward scattering?
Center, at the center, the positive charges.
The positive charge is
Accumulated.
concentrated at the center, and this alpha particle being positive, they undergo repulsion. They undergo repulsion. Maximum repulsion. This is called head-on collision. Head-on collision. So at the what is this distance called? At which
Close
backward
distance
scattering?
of
Distance of closest
close
approach.
approach.
Distance of closest approach. At this distance, entire kinetic energy is converted into potential energy, isn't it? The alpha particle come to momentary stop. The alpha particle come to a momentary stop before it gets repelled away. It goes in the backward direction. Okay. So this is another diagram. So radioactive source, gold foil, and they're all non-deflect, mostly non-deflected particles because most of the atom is empty. And I asked you why this one is only one molecule thick or very, very thin. Suppose if you take a gold plate, very thick plate, what will happen? If you take a many molecular thick gold foil, what will happen? Will the gold foil get scattered like this? The alpha particle may get absorbed, isn't it? The alpha particle, the energy of the alpha particle may get absorbed. They won't come out at all. Okay, they won't come out, or they won't get scattered in different direction if the gold foil is many molecule thick. So it is very important that the gold foil should be very, very thin. Okay. So this what enlarged cross section of the gold foil, many parts are shown. So we can. So in order to make them understand, this is the actually the book diagram. So backward scattering, most of the alpha particles go straight, and you have lead bricks because the lead brick is the alpha particle or collimated as a fine beam. So we introduce a concept of impact parameter, isn't it? Impact parameter and angle of scattering. So here, when the alpha particles, see many alpha particles which are far away from the center of the nucleus. So this impact parameter is a perpendicular distance between the velocity vector of the alpha particle and the center of the nucleus. This is a line drawn along the center of the nucleus, and this is a velocity, different initial velocity vector. It's the direction of initial velocity vector. So this all is what? This is impact parameter. Why important should be given is that in one of the board questions, this diagram is given and they have to tell what is B and what is theta. Such a simple question, but they should know, isn't it? So what will be, if impact parameter is large, what is the relation between B and theta? If B is very large, what will be theta? If B is very large. If B is very large. If the alpha particles are very, very far away from the target nucleus, what is theta? They don't undergo any scattering, isn't it? Theta is 0. Correct? Am I correct? Then if B is 0, what is theta? Suppose the alpha particle is colliding, the velocity vector of the alpha particle is like this. It is along the center of the nucleus. Then what is B is 0, isn't it? This distance is 0 here. What will be theta? If the alpha particle is incident in this way.
180.
180 degree. It will undergo backward scattering. Isn't it? It will undergo backward scattering. So theta is angle of scattering, angle between the incident alpha particle and scattered ray. And this B is the impact parameter. So now at the distance of closest approach, the kinetic energy, the alpha particle undergo backward scattering, and you know that kinetic energy becomes equal to potential energy. So potential energy expression is, what is potential energy expression? You know, no, in electrostatic we teach them K, Q1, Q2 by R. So R naught. At this R naught, this potential energy, the kinetic energy of the alpha particle gets converted into potential energy between, what is Q1 here? Q1 is
Q
charge of the
alpha
alpha
particle and the nucleus.
Q2 is
Nucleus.
ZE, nuclear charge. Q1 is 2E, Q2 is ZE.
Okay.
Okay, so K into Q1, ZE is the charge of the gold nucleus. So we say that according to Rutherford model, you know that the entire positive charge is concentrated at the center. So due to electrostatic force of repulsion between this ZE and alpha particle, the charge is 2E. Okay, the kinetic energy gets converted into potential energy. So we can calculate now R naught. R naught will be K into 2ZE square by K. If I know the kinetic energy of the alpha particle, I can find out this distance of closest approach. So this one is an example problem. So here in a Giger-Marsden experiment, we have to do example problem. We do that, isn't it? So all the exercise and example problem in the textbook are very, very important. So in a Giger-Marsden experiment, what is the distance of closest approach to the nucleus of a 7.7 MeV alpha particle before it comes momentarily to rest and reverse the direction? So we can calculate this. So 7.7 MeV is the kinetic energy. 2K ZE square by R naught. From that, R naught can be calculated. So what was R naught value? R naught was found to be 3.84 into 10 power minus 16. It's a tough calculation indeed. But in the exam, one of the board exam, this question was asked. So about 30 Fermi. So now is that what information do we get? So this is slightly greater than, this is a distance of closest approach. This is alpha particle, this is gold nucleus. Actually, this R naught is, I'm getting it as 30 Fermi. 1 Fermi is 10 power minus 15 meter. It is a sum of a diameter or radius of gold nucleus and alpha particle. It's not, it just gives idea about the size of the gold nucleus. Size of the gold nucleus is much, much less than this, isn't it? It should be less than this distance, because this distance is sum of almost equal to sum of radius of alpha particle and gold nucleus. Correct? Am I correct?
Yes, ma'am.
So now what is the size of the atom?
10
Size
power
of the
minus-
atom is 1 Armstrong
10
unit,
power minus 10.
10 power
meter.
minus 10 meter. So now our size of the nucleus is 10 power 5 times smaller. 10 power 5 times smaller than the size of the 1 lakh times smaller than the size of the atom. So you can imagine that you have to give all the size to the students for the students to imagine. So if you consider the size of the atom as 1 lakh something, 1 lakh unit, the size of the nucleus is going to be only 1 unit. So the ratio is 10 power 5, the ratio between the size of the atom to the size of the nucleus. So now, so this is the Rutherford model. So it is also known as nuclear model. Okay, and it is based entirely on what? Classical concept, Newtonian mechanics. Okay, so you have for hydrogen atom. So most of all the models were formulated to explain only hydrogen. It is suitable only for, so hydrogen is a very simple atom with 1 unit of positive charge, 1 unit of negative charge. So he said that the electrostatic, you know that, isn't it? So we have to teach all this. Electrostatic force is equal to electrostatic force provides what? So when you teach this, you compare with some other motion. No, what is that? When you teach, it's a planetary model, isn't it?
Yes,
Do you
ma'am.
compare and teach them? What is the difference between nuclear model and planetary model? What is the similarity? What is the similarity here?
Sun is at the center, like nucleus.
Yes.
Earth
So
is
here we
revolving
take
around that, like electron.
here we take electrostatic force, centripetal force. There, in the case of planetary system, is a gravitational force provides a centripetal force, isn't it?
In this kinetic energy is a negative of total energy only, you know, ma'am.
There also.
But
Not
twice
kinetic
of
energy,
total
potential
energy.
energy. We'll come back. See what potential energy. mv square by r is k square by r square. isn't it? Ke
In
square by
that,
K square by
kinetic
R square.
energy is
So
the negative of total energy.
yes, we'll do that. Half mv square is what? Half mv square is Ke
Ma'am, in the
square by,
top you wrote the relation, ma'am. In that twice minus 2 TE you wrote in this.
maybe it may be wrong. Let me find
2
out.
must be cut in this, ma'am.
2 is yeah.
Oh, yes.
Yeah. So half mv square is Ke squared by 2R. Potential energy is
Twice of total energy.
Ke square by R. So total energy is this one. Total energy is this. So we can find the relation. So kinetic energy is minus total energy, minus of total energy, and potential energy twice total energy. So whatever we do for this holds good for gravitation also. Isn't it? Gravitational potential energy. Yes. So if you substitute, I'm getting anyway, this is the final expression we'll be using even for Bohr's model. Only thing is that we are going to use quantization, isn't it? We are
Yes,
going to quantize the orbit. Why we are going quantizing the orbit? So what are the drawbacks of Rutherford model? What are the drawbacks? It could not
stability of atom is not
stability of
explained.
the atom could not be explained. Okay. So this again an example problem. So every example problem after, see, don't do all the problem at the end. As you are doing the derivation, okay, after every concept, if there are problems, please do that. Do I follow that? Do you follow that, teachers?
Yes, ma'am. Yes, ma'am.
Yes.
Along with the concept only,
Along
we are
with the
taking
concept,
the
if you
example
teach
everything.
now, that concept will be strengthened, isn't it?
Yes,
Good.
ma'am.
Yes. Then you have to necessarily introduce this emission spectrum in hydrogen, isn't it? There is no theory, experimental background, but this is a empirical relation, like Lyman, Balmer, all that. This empirical relation you will be
Spectral
telling the
series of hydrogen atom.
yeah, spectral series of hydrogen atom, but Bohr theory explained all the series, isn't it?
Yes,
Both these, the Lyman, Balmer, and Paschen bracket series were given before Bohr could give the explanation of the atomic structure. But Bohr atomic structure could explain the emission of spectral lines. And the experimental whatever value suggested by Bohr tallied with the wavelength of spectral lines, all the wavelength of spectral lines given by different scientists like Lyman, Paschen, Balmer. Out of this, which one lie in the visible region? The series, spectral series. Which series lie in the visible region?
Balmer series, no?
Yeah, Balmer series. Balmer series is in the visible region, and that all you should tell the children. Lyman is in UV region, and all the other are in infrared region. All the other are in infrared region. So they may ask such question like, find the shortest wavelength in Lyman series.
N2 infinity.
N2 is infinity, shortest wavelength, because energy will be maximum, no? Infinity to n is equal to 1 level. So longest wavelength in Balmer series will be longest wavelength in Balmer series. N will be 3. Very next one, longest wavelength means energy less, isn't it? Adjacent lines, 3 to 2. Similarly, longest wavelength pattern will be n is equal to 4 to n is equal to 3. Okay, such questions are asked often.
Yes, ma'am.
So this is the drawback of anyway Rutherford atom model. You know, you will be telling the children that stability of the atom was not explained because an accelerated charge. There's an accelerated charge. Electron, no? Why accelerated charge? There is an electrostatic force, isn't it? There is electrostatic force. Electron will be accelerated. So electron will be accelerated according to classical theory. Any accelerated charge will emit radiation, isn't it? So they will lose energy, and finally they'll fall into the
nucleus.
But the atom is stable. Atom is stable. All the atoms are stable. So stability of the atom could not be explained. Okay. So you have to explain when you're that is the main concern for Bohr. How to explain the stability of the atom. Okay. So according to Bohr postulate, nuclear concept, the electron, the same thing as Rutherford suggested, electron revolve around the nucleus. But when it is, as long as it is orbiting in stable orbit, he named the orbit as stable orbit, it cannot radiate energy. Okay, so every atom has certain stable orbit in which it can exist.
Non-irradiating.
Non-radiating, very good, non-radiating orbits. And he quantized the angular momentum. Okay, so electron revolve around the nucleus only in those orbit for which the angular momentum is nh by 2
Integral
pi.
multiple.
And of course, spectral series he has to explain, isn't it? He has to explain the spectral series. How does an atom emit radiation? How does an atom emit radiation?
And it's coming from higher energy.
Higher
state to
orbit. When it
lower energy
undergoes
state.
transition, when an electron make a transition from one of its specified non-radiating orbit to another of lower orbit, when it is doing so, a photon is emitted with the energy difference between EI and EF. Initial energy is higher level, lower energy is EF. Okay, so based on this, so these are the textbook thing with the 4. So we could explain the it's a derivation. So you can find Rn. Rn derivation is very important. This time also we can expect. So the students should write how should they, suppose if they if the question is derive an expression of radius of nth orbit of hydrogen atom, nth orbit of hydrogen atom. That's very important. So first centripetal force provides the
Coulomb force, electrostatic
centripetal force is provided by the Coulomb's force. So we get R. Okay, R is equal to Ke square by mv square. This is one R. MVR is equal to, and we are bringing in Bohr's postulate here. MVR is equal to NH by 2 pi. So Rn, here Rn is NH by 2 pi mv. So we have to equate these two. We are equating these two, we are getting V. So this V has to be substituted here. Where we have to substitute? Here. We are substituting here. I am getting R is equal to this value. Okay, and we are getting R proportional to n square.
N square.
R proportional to n square. So if you put n is equal to 1 and substitute all the other values, we'll get radius. Now, what is that called? It's called Bohr's radius, isn't it? That's called this h square epsilon naught by pi m e square is known as Bohr's radius. So if you plot a graph between n and Rn, what type of graph we'll get?
Curve.
Yeah, very good. We'll get a curve like this because R is proportional to n square.
Squared.
N square. So you won't get a straight line graph. So one of the board question, plot a graph between principal quantum number and Rn. This is the thing. So once you know the value of Rn, you know that En we got from Rutherford model, we got the En as minus E square by this. No, just you have to substitute Rn. So we after substituting, we'll get En is inversely proportional to n square. All the other constant, if you substitute, you are going to get En as 1 by n square. So this is for hydrogen atom only. If you derive for hydrogen atom, it is more than enough because syllabus only for hydrogen and Bohr's theory is applicable only for hydrogen or hydrogen-like atom, like singly ionized helium. Singly ionized helium has 2 electrons. If you remove 1 electron, that is like a 1 electron system, or W ionized lithium. Okay, so hydrogen or hydrogen-like atom or ion. So this is En. This is En. So now we are bringing in what postulate is this? Energy, emission of energy. Third postulate. So when I bring in EI minus EF, so EI is negative. And what is the significance of this negative energy? What is the significance
There is
of
an
negative?
attraction between the nucleus and the electron.
There is attraction. So
Yes,
can the electron jump away? If it has positive now, electron will be eliminated from the atom. So electrons are bound. That's very important. So the negative significance of negative energy is that electrons are bound to the nucleus. Otherwise, electron will fly away, no? Isn't it? So
Like
if you want,
gravitational potential energy.
even this total energy of planet is also negative. Otherwise, planet all will fly away from the sun, isn't it? Any attractive force will lead to negative energy. Okay, so that what is ionization energy? Ionization energy for hydrogen is plus 13.6 electron volt, isn't it? It is plus 13.6. Energy required to remove an electron from the ground state of hydrogen. That is only ionization energy. So we get this formula called Rydberg formula, isn't it? EI minus EF is this value 1 by NF square minus 1 by NI square, because it's EI minus EF, both are negative. You have to make the children remember the formula. And this one is EI minus EF is H nu. So you will write this as Hc by lambda. So this will be very useful formula. 1 by lambda is R into 1 by NF square minus 1 by NI square. Okay. Ni is higher orbit, NF is lower orbit. So this will be positive. So you should also ask the children to memorize these values because it will be very useful. So you let them substitute N is equal to 1. So E1 is minus 13.6 eV, that is ground state. So we call this E2 as first excited state.
N
So
is equal
please,
to 2.
children, yeah, N is equal to 2. Ground state is N
That's
is
what
equal to
the
1.
children not remembering this, ma'am. Ground state, they will put a N is equal to.
Yeah. That's why you have to
Excited
make
state
them
means
understand.
they will put N
Yeah,
is
very
equal
good
to
point.
1.
Yeah, yes, N is equal to 1 is ground state. It is not N is equal to 0 does not exist at all. Okay, N is equal to 1 is a ground state. First excited state is 2. The second excited state is N is equal to 3. So let them remember these values at least. Otherwise, they can also calculate at least this formula. They should remember final formula. So all this formula. So then you try to explain them after introducing this one. You just explain. Now we have already Lyman that those empirical formula can be derived from this formula. Lyman, Balmer, Pachon brackets, these can be derived. See, you can you should also from this diagram you should also bring out one important point that as n increases, the lines become closer. The lines become closer. That means energy difference become less. Energy becomes less. So limitation of Bohr theory. This theory is applicable only to hydrogen-like atoms. Okay, and in spectral lines, certain spectral lines are not single line but a group of closed lines. Bohr's theory could not explain these fine feature of hydrogen spectrum, and why only circular orbits are chosen when elliptical orbits are also possible. And you should also explain about splitting of spectral lines in magnetic field and electric field. Okay. An electron exhibit wave properties, so orbit of electron cannot be exactly defined in Bohr's theory. You know that then later on de Broglie explained the way he incorporated wave motion of electron in atomic structure, isn't it? That is also important question. We'll discuss when we are discussing questions, we'll discuss that. So what is first excitation energy? E2 minus E1 is the excitation energy of an atom is defined as energy required by its electron to jump from ground state to any one of the excited states. So if you want the electron to jump to higher orbits, higher energy levels, you have to supply energy. So if you supply 10.2 electron volt of energy, the electron will jump to second level. Okay, that is a meaning. Ionization energy is energy required to knock an electron completely out of the atom. So it is E infinity to E1. That is only ionization energy. E infinity is 0. At infinity, energy is 0. Minus of minus 13.6 eV. So ionization energy is 13.6 electron. So ionization potential is energy is 13.6 electron volt. Accelerating potential. So how to knock out the electron? You have to provide some potential. Okay. So that what is that potential required to knock out the electron? It is 13.6 volt. So you can always have a concept map. And this one, de Broglie explained this, isn't it? So electron is not only moving along a circular path, it exhibit wave-like characteristics. So already a wave nature of electron is experimentally, it was proved by Davison and Germer. So the electron, it is what type of wave is that? It is is it a progressive wave? I've given one more illustration here. What is the type of wave here?
Standing.
Stationary wave. It's a stationary wave because this wave is confined within certain 2 points. So when you teach stationary wave, if I have a thread here, I can make a wave to this. If I pluck it at the center, this is an incident wave and this is a reflected wave. So wave is confined within this. Even electron is confined within the orbit, isn't it? Wave is restricted.
Nodes and antinodes.
Yeah. So nodes are at fixed position. See, this is waves in a string. Whereas here, nodal point and antinodal points are created, fine. But here, you have to make the children imagine that this orbit as a fixed length. So it should be only stationary wave. So you have a wave and then it is reflected and you have another wave superposed on it. So what type of wave can survive? What type of wave can survive? The waves where integral multiple of lambda can exist. Circumference of the electron orbit. The circumference of the electron orbit should be an integral multiple of wavelength. Only those waves will survive. Others, suppose if it is this condition is not satisfied now, destructive interference will take place. The waves will not survive. So this is the condition. So n is equal to 1, only one wave. For first orbit now, only one wave. This is 3 waves. So this number of waves is possible when n is equal to 3 waves are possible. Then what will n? Here 3 waves are possible. N is equal to 3. Okay. See now here the wavelength forbidden orbit. Why forbidden orbit? The number of waves 2 pi r is not equal to n lambda here.
Condition is not satisfied.
Condition is not satisfied. So we can write. Let us see whether we are bringing this a de Broglie wavelength. It's a matter wave. Electron is a matter. So in place of lambda, I can write h by mv. So we are getting mvr is equal to nh by 2 pi. So we are bringing, by considering electron as a wave, we are able to bring in force quantization condition. Isn't it? Okay, now I'm going to switch over to questions. What type of board questions are asked here? You can also use it for your revision, no? For the children. This PPT will be very useful. Write important inference drawn from Rutherford model. What are the 2 important inferences? What are the 2 points you will write? What are the 2 points you will write here? Most of the space in the atom is empty. So what is the experimental evidence for this? Most of the alpha particle, what was the trajectory? Went straight, isn't it?
Yes, ma'am.
Went straight. Okay, this is the evidence. Then second important thing is positive charge
are in the center.
Concentrated at the center
of the atom is concentrated in a very small volume. That is very important, isn't it?
Yes,
Nuclear size is very, very small.
Into the
yes, or minus 15.
At the center of the atom. Center of the atom. But what about the size of the positive charge? Very, very small. These are the 2 points. Okay. The kinetic energy of alpha particle incident on a gold foil is double. How does the distance of closest approach change? What is R naught formula? 2E ZE Q1 Q2 K by K, isn't it? This is the formula for the distance of closest approach. How does the, so now I am changing the doubled. So R naught dash will be 2K, isn't it? 2K ZE square by 2K. So R naught, what is this?
Becomes
R
half.
naught becomes half. Becomes half. Okay, this was a question. The trajectory traced by different alpha particle in Geiger-Master experiment were observed as shown. What name are given to the symbol B and beta? What is B? What is B? It was one question for 2 marks. This was asked. B is
Impact parameter.
impact parameter. B is impact parameter.
Theta scattering angle.
Scattering angle. Theta is scattering angle.
Scattering angle.
In the study of Geiger-Master experiment on scattering of alpha particle by a thin cold foil, draw the trajectory of alpha particle in the Coulomb field of the target nucleus. So let us see how we should split the mark for this. Explain briefly how one gets the information on the size of the nucleus from this study. What are you going to write? So you have to give the trajectory of alpha particle.
You have to draw.
You have to draw. For drawing, we can give, suppose this is a 3-mark question. Okay. 3-mark question. How one gets information on the size of the nucleus from the study. So now, let me draw this. So this is a gold nucleus. So let us say this has a gold nucleus because it's given as gold nucleus. So I will draw correct. This one. So the children will draw this, and here this is the backward scattering. So give them children practice of drawing the diagram. So the alpha particle which are very close will undergo large angle scattering, and the alpha particle which are very far away will go straight, and the alpha particle which are colliding head on, this is alpha. Okay, and so at the distance of closest approach. So this, if the children draw, you have to give 1 mark for this. And then explain briefly how one gets information on the size of the nucleus from the study. So let definitely that distance of closest approach formula they should write, isn't it? At the distance of, so you, the children should write when the alpha particle strike the gold nucleus head on, that is head on collision. That is it is a line. The velocity vector is along the center of the nucleus, the velocity vector. So this distance is r0. Okay. At r0, what happens? The kinetic energy. So what happened? They have to write this. Alpha particle experience force of repulsion and the reverse backward scattering occur. So at the distance of closest approach, when alpha particle undergo head-on collision, the entire kinetic energy, because of the force of repulsion, they experience maximum force of repulsion and the alpha particles are turned back. If they give this explanation, you should give half mark. At r0, due to the force of repulsion, the alpha particles turn back and they undergo backward scattering. So for that, you can give half mark. So 1 mark is given, half mark is so kinetic energy is equal to potential energy, and then deriving the expression for R0, 2K ZE square by kinetic energy. This can be given as 1 mark, and giving the approximate value. So how one information R0 was found to be about roughly 30 Fermi or 40 Fermi also they can write. This R0 was found to be of the order of 30 Fermi or 45. I think they can write depending on the kinetic energy that this will be 30 to 46 Fermi. That value is also given in the thing. The size of the nucleus, ideal, just Rutherford experiment. From Rutherford experiment, we could not measure the radius of the nucleus. Radius of the nucleus was measured by using electron as a target. You know that, no? In the nuclear lesson, this is coming. Electron as a target, scattering with the electron as a target and trying with different atom. The nuclear radius of different atoms are successfully determined. One word is coming. Okay, so this just give this Eager-Marsden experiment gives us an idea about the size. It's less than 30 Fermi. Okay, because atom size was measured, it is at 10 power minus 10. So it was shocking for them when they got the R naught to be of so low value. So this way it has to be split. Okay. This question. Explain why the spectrum of hydrogen, this is again a board question. Explain why the spectrum of hydrogen atom has many lines, although a hydrogen atom is only one electron. So you get many lines, no, Lyman series, Balmer series, Faction, Fund. Why? Hydrogen atom has only one electron, no? But this one electron can occupy, see, if you take a source of hydrogen spectrum, say hydrogen gas, and if you excite it, suppose you fill the hydrogen gas in a tube and then have 2 electrodes and then very high potential difference is applied, V. What will happen? There are millions of hydrogen atom. So each atom has many stationary state. So though hydrogen has one electron, allowed stationary states are many. N is equal to 1 to infinity. So electron can be in any of the state. When we provide energy, electron can be N is equal to 1, 2, 3, 4, 5. Innumerable number of energy states are possible. So all possible transition can occur from any higher level to any lower level. That is the reason why spectrum of hydrogen atom is many lines, although hydrogen atom is only one electron. So have you ever seen this question? I have seen in a board paper. Okay. So a source of hydrogen spectrum has billions of hydrogen atom. Each atom has many stationary state. All possible transition can occur from any higher level to lower level. Then, depending on the energy difference, spectral lines of different wavelength can be emitted. Isn't it? Yes or no? Correct? Do you agree with me? Is this answer correct? Yes.
Yes, ma'am. Yes.
And this is very often asked question. Using Rutherford model of the atom, derive expression for the total energy of electron in hydrogen atom. What is the significance of negative energy possessed by the electron? So we already derived this expression, no?
Yes, ma'am. Yes,
So
ma'am.
how, suppose this is 3-mark question. How will you split the mark?
Kinetic energy, potential
so-
energy, total energy. Then they have to give the
So
answer
they have
for
to write, centripetal force is equal to Coulomb force.
Coulomb
K
force.
is it K E square by R square. So this for this half mark can be given. Then half mv square is equal to K E square by 2R. For this half mark can be given. And potential energy is equal to minus K E square by 2R. 2R. Correct? R. Sorry, R. Sorry, R. So total energy is, this is half mark. Total energy will be minus Ke square by 2R. So here, one half mark. So what is the significance of negative energy possessed by an electron? Negative
Electron
energy
is bound to the nucleus.
For that,
Yeah,
1 mark can be given. Reasoning question. So 3 marks. They're splitting the 3 marks. Sometimes they give half mark and they give this total energy. Somewhere they introduce 1/2 mark. That is possible. So some paper you can see this half mark only for the significance. Depends. So using Bohr postulate, derive the expression for radius of nth orbit of electron. Please make them practice this derivation for sure, because many portions are deleted, no, in atoms. Radioactivity is not there. So hence obtain expression for Bohr's radius, showed graphically the variation of the radius of the orbit with the principal quantum number. So we'll just take the marking scheme for this. Radius radius of the electron. So can we give 2 mark for this?
Yes, ma'am.
And graph
We have to graph 1 mark.
1 mark, 1 mark. And then this itself can be split. There are many steps for Rn, isn't it?
Yes, ma'am. Yes.
There are many steps for Rn, as we discussed. So that has to be split. So students, even if they go in the last step,
Velocity is also they will ask. the ma'am along
velocities.
with that.
But most popular question is
Sometimes-
radius. Sometimes they may even
Okay.
ask. Anyway, we have to get velocity now here. Velocity expression we should derive here itself.
Yes, ma'am. Yes.
This one also often they're asking. Using Bohr postulate of quantization of angular momentum, show that the circumference of the electron in the nth orbit in hydrogen atom is n times the de Broglie wavelength associated with it. So you have to use Bohr's postulate. Okay. First you have to start with Bohr's postulate. MVRN is equal to NH by
NH by
2 pi.
2 by.
Then what we should do? We have to find out 2 pi Rn is equal to n lambda. We have to arrive
Circumference
at
of
this.
an electron 2 pi r is equal to
2 pi from this. 2 pi Rn is equal to NH by Mv from this. So what is H by
Lambda.
Mv? N lambda. H by Mv is n lambda. It is a other way it is asked. Other way. So we can get this expression. Using this we can get this, or using Bohr's postulate we can derive this. The electron in hydrogen atom is initially in the third excited state. What is the maximum number of spectral line which can be emitted when it finally moved to the ground state? How many? Third excited state means what?
n equal to 4.
3, 4. Third excited state. So electron is here. Okay. What is the maximum number of spectral line which can be emitted when it finally moves to the ground state? So it can come to this
3.
state from here, or it can move to the. So what are the possible transition? This one. 3 is transition only.
Yes, ma'am.
Only 3. Why not? See, after undergoing here, it can undergo transition from here to here, no? Correct? This is A. B transition is this. C's transition is this. This is D transition. One more transition. From here to here, it can come, isn't it? That is
Then
E
another-
transition. E transition. Which
2
is
to
another
1.
one. One, two, two. Yeah, from here to here. Actually, if n is equal to 4 now, number of transition possible is n into n minus 1 by
n
2.
minus 1.
4 into 3 by 2. 6 transition. So you have to draw. Children should draw the transition. Anything we missed? So 4 to 1, 3 to 1, 2 to 1.
6.
Okay. 4 to 3, 3 to 2. We missed 4 to 2. Correct? This one is repeating. This one is not it. Correct? 4 to 2 also possible, isn't it? That we missed. Am I correct?
Yes, ma'am.
4 to 1, 3 to 1, 2 to 1. 4 to 3, 3 to 2, and 4 to 2. Okay. Suppose this is a question. How will you start? There are 2 ways to draw this, to do this question. The energy level diagram of an element is given below. Identify by doing necessary calculation which transition correspond to emission of spectral line of wavelength 102.7. Which is the easiest way? Will you find the wavelength corresponding to A, B, C, D? And then find the, how to do that? will you find out the energy difference, and then I minus EF is equal to HC by lambda, and then finding lambda and coinciding with and checking whether it is with 102.7 or this method. So I always teach the children to do like this. See, 102.7, what is the energy corresponding to this lambda? So you know that it is HC by lambda. So after calculation, I'm getting 12.04 electrons. So this is a one-step problem. So convert that into electron volt. Ask the children to convert into electron volt. It is about 12 electron volt. So which transition, which energy difference, the energy, the transition correspond to energy difference of 12.1. It is between 1.5. See here, if you consider minus 1.5 D transition, minus of minus 13.6, isn't it? Minus 1.5 minus of minus 13.6. This comes out to be about 12.1 electron volt, positive energy. Correct? So always whatever wavelength is given, convert that into energy, energy to be converted into electron volt, and then check which difference in energy. It is easy to find, isn't it? Than to calculate this calculation for every transition. What method do you suggest to the students? This method, or for every transition you ask the students to calculate the wavelength?
This method is easy.
This method is easier.
Yes.
This method will be easier. Always find out the energy corresponding to the wavelength, and then this one
We have
matches
to
with
find
what
the energy difference.
Energy difference, that's all. And here, see, what is the difference between emission and absorption? See here, it is given the above arrow. See, suppose here, see the question here. This is also one board question. Photons with a continuous range of frequency are made to pass through a sample of rarefied hydrogen. So now when you, if you take a hydrogen filled gas and if you pass high potential difference, emission spectrum is obtained. So what is that absorption spectrum? How do you get that absorption line? What do you mean by absorption line?
Ground to excited state.
If you supply energy now, if you supply energy,
it takes
the
energy
electron
and it
will
will move to the excited state.
Yeah. Suppose you have a hydrogen here. Hydrogen, it's not excited. Hydrogen. And photon with a continuous range of frequency. You are passing white light. So white light will have all the frequencies, isn't it? White light is a composite light. So now white light is passed. That is only photons of continuous frequency pass through a sample of hydrogen. So this is a sample of hydrogen. The transition shown here indicate 3 of the spectral absorption. How will you identify between the emission spectrum and absorption spectrum? Emission spectrum, you will get bright lines. Suppose these are the lines obtained. Okay. In absorption spectrum, when you are passing white light through a hydrogen, you know that good emitters are good absorbers. A gas which can emit certain wavelength when it is excited can absorb the same radiation when white light is incident on it. So in place of what happens is you will get corresponding to where these are dark lines. What is the dark lines? So if you analyze the light, if you analyze this light, no, after passing through hydrogen, this light would have lost some of the wavelength. Why did it lose? The spectrum will be, you will have corresponding to these lines, there will be dark lines. That means this hydrogen has absorbed those wavelength which it could emit when it is excited. Okay. So that is only the difference between emission and absorption spectrum. Okay. So now what is this absorption spectrum here? This one correspond to, what is the name of the absorption spectrum? Identify the spectral series of hydrogen emission spectrum to which of these 3 lines correspond. So these, see these lines. So these lines correspond to some absorption has taken place. We understand that absorption has taken place. So there are some dark lines. So you will get some dark lines here. What is the spectrum? What is the name of the spectrum here? It is starting from n is equal to 1 to higher level. Here it is n is equal to 2 to higher level, n is equal to 3 to higher level. What is this line? The transition indicate 3 of the spectral absorption lines. So now the hydrogen has absorbed some of the lines, some of the radiation. So when it is white light has some energy. So when energy consisting of all the frequencies is incident through the hydrogen gas, this hydrogen gas has absorbed certain lines. So what is this? So see, when it is a emission spectrum, what do you call this line as? What do you call this line? Lyman.
Lyman.
So this one will correspond to Lyman. What is asked here? Identify the spectral series of hydrogen emission spectrum to which each of these 3 lines correspond. Okay, when the hydrogen is excited, okay, it will emit radiation correspond to Lyman. So when the same energy is incident on it, it will get excited to higher energy level. So this one will be second correspond to
Palmer.
Balmer. Third correspond to Patchen. Which of these lines correspond to absorption of radiation of maximum wavelength? Maximum wavelength means minimum energy, no? Minimum energy, isn't it? How do you identify that?
Third one.
Third one.
Energy difference
So you
is
should
minimum.
energy difference. So here this one is 13 minus 13.6. N is equal to 2 correspond to what? We don't know. Yeah. Minus 13.6 minus 3.4 minus 1.5. This is n is equal to 3, n is equal to 2, n is equal to 1. So I think the energy difference you have to find out. What is that? Minus 1.5 plus 3.4 will be what? 9. It is 1.9. So this transition is 1.9. This transition is 1.9. Whereas this corresponds to Balmer. 13 minus 13 points. Okay, what is the other transition? 4 to 3, no? Isn't it? 4 to 3. 4 n is equal to 4 is 0.85. 0.85 and it is 1.5. N is equal to 3 is 1.5, all negative. So if you calculate, find the energy difference and we can prove that the third transition corresponds to minimum energy. Why is classical model of atom? This is again another good question. Why is classical model of an atom of electron orbiting around the nucleus not able to explain? Classical model means it is Rutherford model. Sometimes they won't even give Rutherford. Classical Rutherford model is based on classical model. That why it is Bohr's model quantum na? Because he is using no EI minus EF is equal to h nu and he has quantized the angular momentum. That is discrete. The values of angular momentum, they have fixed angular momentum for each orbit. He has fixed the angular momentum. That's why it is quantization. Quantization means assigning discrete values, not continuous values. Okay. So as the revolving electron loses energy continuously, it may spiral inward, eventually fall into the nucleus. So it was not able to explain the stability, not atomic structure, stability of atom. Okay, this is again another question where it is, if you are, suppose you are given a chance to repeat the alpha particle scattering experiment using thin sheet of solid hydrogen. Okay, so you are using thin sheet of solid hydrogen in place of the gold foil. Hydrogen is a solid at below 14 K. What result do you expect? What do you think? Alpha particle, if you consider alpha particle here, if you consider gold, it's much, much heavier. Correct? Whereas alpha particle, and if you take hydrogen atom, H. So you have to imagine the size now. So what will happen? Will alpha particles, see why you get different trajectory of alpha particles, some undergo, some they don't undergo. If you consider the gold nucleus to be like this, Okay, this is a nucleus. So different trajectory we expect now. Like this and then, isn't it? Can it happen if you use instead of gold nucleus, hydrogen? Can the backward scattering occur? So only because of the backward scattering, the scintillation. So in the fluorescent screen, scintillations were observed in the exactly in 180 degree. No, is it possible if we use hydrogen as a target? It's called target nucleus. What will happen if alpha particle is striking like this? Will it see? It is only because of the force of repulsion between alpha and ZE, 2E and ZE. The repulsive force is very, very high. It is at the distance of closest approach. It is rebounding in the backward direction. Is it possible for hydrogen? Is that much repulsive force will alpha particle experience? Please tell me.
Will not rebound.
It's not possible. No, Ramesh Babu sir. What do you think?
It's not possible, ma'am.
It's not possible because hydrogen being very light, isn't it?
Yes,
So it
ma'am.
will just penetrate. For all the alpha particle will penetrate the hydrogen.
Yes,
So you won't get any specific result at all, isn't it?
yes, ma'am. Yes,
So
ma'am.
the target nucleus is lighter, from which we can conclude that alpha particle would not rebound. So it was possible for Giger and Marsden to calculate that R naught only because of the backward scattering, isn't it?
Yes, ma'am.
Yes. Now it is not possible because hydrogen being very light, the repulsive force experienced by alpha particle and
Not
hydrogen,
rebound.
yes, will pass out. The solid hydrogen is not suitable replacement to good foil for the alpha particle scattering experiment. Now scattering will not take place. Back different angle scattering will not take place. Very, very light. Target nucleus should not be light at all.
Okay, ma'am.
So such type of question also asked. Calculate the shortest wavelength in the Balmer series of hydrogen atom. So you should make the children understand this, or they should memorize this formula. And they should write the formula like this. Though, see, they may get confused. What is EI minus EF is H nu. And you know that EI is greater than EF. Whereas, and EI is negative. All the energies are negative. EI is less negative, so it is its value is more. Correct? As you go to the higher orbit, negative value decrease, na energy is more. Okay, so shortest wavelength, na? Shortest wavelength, na? More energy. That means Ni should be infinity. From the transition occur from highest energy level to lowest energy level. For Balmer, lowest energy level is 2 square. Okay. In Balmer series, electron jump from higher orbit to the second stationary state. Okay, this is the answer. So 1 by lambda is R by 4. And they can even remember this R value. 1.097 into 10 power 7. They can write this as 1.
Constant.
Yeah, Rydberg constant, they can write, no problem at all. They can write 1.1 into 10 power 7. 10 power 7. And see here, it is visible, na? It's not ultraviolet, it is visible. All the Balmer series are in visible region.
Visible region.
Again, here only N is given. Find the transition which results in the emission of photon of wavelength 496.
Convert that into energy.
Convert that into energy. Convert that into energy, and the children should know. What is this? See here. The children should know that these are the energy levels. See here, E1. E1 is equal to minus 13.6, E2, E3, E4. So 2.5 electron volt. So it is nearly equal to
E4 minus
E4 minus E2. E4 minus E2 is 2.5 electron volt. Okay. So alternatively, the student calculate the mark can be given even if they use the Rydberg formula, but it is a laborious process. Any correct method, we have to award mark. Okay.
Any method.
Any method correct, we have to give mark, though it is a laborious method or whatever method which is correct. So suppose if the child write only formula, you have to give formula. Correct substitution, mark should be given. Okay. And the child, most of the children will not convert that into electron volt. Maybe if they convert this into joules and they match that, for that also mark to be given. But always train the children in a way which can save their time. Because
Okay.
this is a lot of calculation. So this is the best method. Convert the wavelength to energy and let them find the difference in the energy level which are mentioned. Whichever is matching, let them write that as an answer.
Okay.
Okay. Find the relation between wavelength lambda 1, lambda 2, lambda 3 from energy level diagram. So you know that. Let them children not write lambda 1, lambda 3 is equal to lambda 1 plus lambda 2. No, it's not correct, isn't it? So the ECA will be equal to ECB. Energy radiated between the transition C and A is equal to ECB plus EBA. So you know that EC H nu 3, isn't it? H nu 3 is equal to H nu 1 plus H nu 2. Let them write this as HC by lambda 3 is equal to HC by lambda 1 plus HC by lambda 2. They will get this answer. So 2 or 3 times this question was asked.
Yes.
Very easy.
Revision also asked, I think.
Yes. Revision exam, we have given this. So now see theory question. Draw the energy level diagram of hydrogen atom. So we should not focus only on problem. Draw the energy level diagram of hydrogen atom. The atom in its ground state is excited by absorption of radiation. How many different kind of lines are possible in the emitting spectrum? Calculate the longest wavelength among them. So all these details are given. So they will draw the energy level diagram. So now, what is that? Radiation as a wavelength 970. So how many different kinds of lines are possible? First of all, so we have to find out what is the energy. So Hc by lambda. The energy Hc by lambda, if you substitute and convert to electron volt, I am getting it as 12.75. Okay. So now energy absorption. So when you are not supplying energy now, what will be the energy of the hydrogen E1? Minus 13.6. So when you are supplying energy by
970.
radiation, 970 Armstrong unit. Okay, 970 Armstrong unit. So you will find out E is equal to Hc by lambda. And then you have to convert into electron volt. You will get the answer as 12.75. So this much energy is given now. So add this. Okay. If I add, I'm getting it as minus 0.85. So minus 0.85, you know that correspond to n is equal to 4.
4.
So electron is getting excited to n is equal to 4. Either the children can use the formula n into n
N
minus
into n minus 1 divided by 2.
or suppose if they don't remember the formula, all possible transition they should write like 4 to 3, 4 to 2, 4 to 1, 3 to 2, 2 to 1, 3 to 1. All the possible transition, we know that it is 6 lines. Please make the children practice this type of problem.
Okay, ma'am.
6 lines. Okay. So what is that? Another question. See here, so many questions are here. This is really a hot question. The hot question doesn't mean that it has to be difficult. Hot question means higher order thinking. Many in the concepts are interrelated. So with the same question, if different concepts are being tested, different learning outcomes you are testing now, that's the hot question. You are asking them to draw. You are going to you are also teaching their calculation level, skill, reasoning level. Calculate the longest wavelength. What will be the longest wavelength? Shortest energy. Longest wavelength is shortest energy, so it should be between the adjacent level. Okay. So remembering the energy level of an hydrogen spectrum is very important, and then they should calculate. Actually, they should calculate, and then they should decide. Okay. They are finding the energy difference. Again, calculating the lambda value. See, at least if the children goes wrong in the calculation, fine. For half mark, they will lose. But writing all the formula, for each formula, mark will be given. the child is writing energy differences E4 and E3. So the child has identified this is a transition. Maximum mark we can go for this. Again, for this half mark, only for the final calculation, we need half mark. So ask the children, see what the children will do. No, they will write the formula elsewhere as a rough calculation. Formula should be given important. Ask the children to write the formula, substitute the value, even if they go wrong in the calculation, let them not
Can
lose
you
mark.
show the problem once again, ma'am?
I'm going to, if you want, you can
Longest
send to your
line.
children also. I'm going to put it in the group. Okay. Then
Okay,
I'm
ma'am.
going to use,
Okay, ma'am.
you can send to the children. Solution is also there.
Yes, ma'am. Problem
Okay,
is the solution.
so I'm going to do the these problem revision for my children as soon as their English exam is over.
Yes, ma'am.
So before the exam, whatever revision we do know, their absorption will be better. I think you
I
must have
already
please send
experienced
in
it,
the
isn't
group,
it?
ma'am.
Such kind of problems I already revised.
Huh?
Ma'am,
Like
please
such kind of
send in
problems
group,
I
ma'am.
revised, ma'am.
Yes. Yeah, we
Ma'am.
have done, but just before the exam, if you do
We
know,
have to recall everything, ma'am.
yeah, they
But
have to
there is no
recall and you
enough
have to stress
time.
again.
6
You
days
have time.
only there.
You
Ma'am,
have
please
no
send-
call. I'm going to call the children. Week once, I'm going to call and then I'm going to sit with them and make them learn.
Ma'am, please send in the group, ma'am. This
Yes,
problem and
definitely.
solution.
Definitely, I will send. Definitely I will
Okay.
send. So this question, so I'm coming to the nucleus. I thought these 5 or 6 questions are very important. What is the size of a nucleus? Experimentally determined. Write the relation between the radius and mass number of the nucleus. Show that the density of the nucleus is independent of its mass number. So all a theory question. So now size of the nucleus experimentally determined. Of course, we got the idea of size of the nucleus, size of the nucleus from Giger-Marsden. But by performing scattering experiment in which fast electrons instead of alpha particles are projectiles that bombard targets made up of the various elements, the size of nuclei of various elements have been accurately measured. So you should make the children understand that it is not because of Giger-Marsden experiment. It was repeated by what is a projectile now? Projectiles are not alpha particle. Projectiles are electron, fast electron. Okay, these fast electrons are used as a projectile that bombard targets made up of various elements. The size of nuclei of various elements have been accurately measured. So this will carry 1 mark. So it has been found that nucleus of mass number A is a radius R. So R is equal to R naught. This is the result. A is the mass number and R naught is 1.2 into 10 power minus 15. So what is the proof for this? Nuclear density is constant. How will you prove this? Density is
Mass by volume.
Mass by volume.
4/3 by R cube. Or instead of R cube, we have to substitute R naught A power 1/3.
M into A. Correct? Mass of the nucleus is mass number into mass of the nucleon, isn't it? Ma. R naught cube into A. Correct? Am I correct? So this will be 3m by 4 pi R naught cube. So it is independent. We prove that it is independent of mass number. The mass of any atom is m into A, no? A is the mass number and mass of the nucleon. Nucleon is either proton or neutron. We don't differentiate between proton or neutron. Suppose oxygen has 16, mass number 16, 16 into 1.6 into 10 power minus 27. So the density of nucleus is a constant. This proof may carry 1 mark. 2 nuclei have mass number in the ratio 1:8. What is the ratio of the nuclear radii?
1:8.
1:8 are nuclear radii.
Radius. Mass number.
R is equal to R naught.
A
R naught
power
A power
1/3.
3.
R1 by R2 will be
1:2.
1 by 8 to 1 by 3.
1:2.
So 1 by 2. 1 by 2. So very frequently asked question.
Yes, ma'am.
Draw, and this is very, very
Sometimes
important.
they ask the density, ma'am.
Density, yeah. What is the ratio of then density na nuclear 1:1? That's what you should not be. Students should
1:1.
not be in a hurry. That's what I even when we do calculation, we'll be in a hurry and we'll make mistake when we are teaching. I used to tell the children, see, when we are in a hurry, we make mistake. So always it's better you check the previous step. You go, see, after every step, check the previous step whether you have done it correctly. It's not going to take more than 10 seconds to check. Draw a plot of potential energy between, because binding energy curve is not there. I think they may ask this potential energy between a pair of nucleon as a function of mass number. They may ask. Mark the region where potential energy is positive or negative. So whenever they are plotting the graph, definitely the potential energy should be in MeV. They should write that. And the distance should be in Fermi. All this you should tell the children, you should instruct the children. Whenever they draw the axis, they should give the proper unit here. Because so this potential energy MeV million electron volt. Why? The strong value of potential energy suggests that the nuclear force is very, very strong, isn't it? They may ask characteristic of nuclear force. Okay, this 0.8 Fermi, 0.8 Fermi is R0. 0.8 Fermi is R0, where the energy is 0. The energy potential energy becomes 0. Suppose if I take R less than R0, R greater than R0, R less than R0, potential energy is positive. R greater than R0, potential energy is negative. Sometimes they ask the nature of the force. Here, R greater than R0, what is the nature of the force? 0.8. See here, you are imagining this potential energy, we are imagining two nucleons here. One nucleon here, another nucleon is brought. So gradually I'm bringing another nucleon close to this nucleon. So a nucleon is either proton or neutron. So as the distance decreases, what happens? As the nucleon approach, the attractive force increases. It attains maximum. Here it is 100, minus 100. This is plus. But at the equilibrium, the attractive force become minimum. Maximum here, sorry, minus 100, and later on the attractive force decreases. It becomes lesser and less negative. And when it R less than R0, the force is repulsive. This is attractive force and this is repulsive force. So for distance greater than 0.8, negative potential energy goes on decreasing and shows attractive interaction. So this is how the explanation is given. You have one nucleon at the origin, another nucleon is brought closer. So as the distance changes, how the force between them change. So when the distance is more, it is attractive. When the distance become less, when they become very close, it becomes repulsive. Otherwise, we cannot account for the stability. This graph is very important. So this the question I picked up. Obtain approximately the ratio of the nuclear radii of gold isotope and the silver isotope. Gold isotope and silver isotope. I know the mass number 197, 107. So radius R by R gold by R Ag will be what? A1 by A2 to the power 1 by 3. Correct? 197 by 107 by 1 by 3. Very tough calculation. If they use logbook, it is not a problem. 1.84. You can use the log. 1.23. Can they ask binding energy? Is it there? What do you think? So this is a given coin. This is a textbook problem. A given coin has a mass 3 gram, calculate the nuclear energy that will be required to separate the neutrons and protons from each other. For simplicity, assume that the coin is entirely made up of copper. So they should give the data of, so copper has 63, 29 proton and how many neutron? 34, na? 34 neutron.
3 minus 29.
34 neutron, 34 neutron. But you should find out 33 gram, la, how many atoms of coppers are there? So you know mass of, so you can find out binding energy of one copper atom. That you know how to find out. So binding energy is, so required energy you have to find out for 3 gram, you have to find out for 3 gram. So 63 gram contain this much. So 3 gram will contain this many atoms. This many atoms are present in 3 gram of copper. So 1 atom of copper releases this much energy. So required energy is this much. Of course, this is a little tough problem. I don't think they will ask.